Very good. It's a great pleasure for me to welcome all of you in this section on quantum communication. And well, today we have a great actor, great pioneer in the field that essentially is paving the way to technology. We are lucky in the sense that still this field show the need of new experiments to provide elements, concreteness to the technology that will come. This is the path that was followed in the past. So we had pioneering experiments in the 90s and technologies in the decades that after, and still we are in this phase. And for this reason, it's of great interest to hear from the scientists that are working on these aspects about the progresses. We have three outstanding scientists in this session, and the first of this is coming now. Is Professor Hugues de Riedmatten, that is professor at ICFO in Barcelona, and without further delay, I would like to give word to Hugues for his talk.
Thank you, Paolo, for the introduction. Let me share my screen. You should see my slides now.
Indeed, yes. Please.
Okay, very good. So thanks for the introduction. It's a pleasure to talk at this conference and to start this morning session. I'm going to be talking about our recent progress to build quantum repeater architectures that we have done at ICFO in Barcelona, but also more generally in the quantum flagship. So let's start by the long-term vision. The long-term vision would be to be able to have a system that can distribute entanglements between any 2 points, ideally on the planets, but let's start, let's say, by continental scale. And so what we would like to have is a system that can distribute entanglement. So this would look something like this on a type of quantum network. This is what Jeff Kimball called the quantum internet. So what we would have is material quantum nodes, which would be small quantum processors, or they could be also big quantum processors, that will share entanglement now using photons at telecom wavelength, for example, in optical fibers. And if we could do that, then there are a lot of new cool applications that we cannot do with the classical internet. The most known is, of course, being able to do secure communication using quantum distribution. We can also have some slightly more futuristic applications which consists, for example, in connecting quantum computers or doing blind quantum computing. If you have a centralized quantum computer, for example, that you want to access in a secure way. And there could also be some other type of applications more in metrology, for example, making some telescope arrays with better resolution, of having networks of clocks with better synchronization and better precision. So if we want to now look on one of this link, if you want to send entanglement within this link and store it into some quantum memory for future use, one thing you could do is directly to send the single photons in the optical fiber. But of course, fibers have loss, and after, let's say, 100 kilometers, you will lose 99% of your photons. And so there are two ways to overcome this problem. One way would be to use, for example, satellites. Our Chinese colleagues have done some really interesting work in that direction, and I think Europe is also preparing its own mission. But there is another complementary way, which is to stay within the fiber network and to use quantum repeaters. So how does a quantum repeater work? The idea is to separate the total distance into several links. I show here 2 different links, but there could be in principle more links as well. So then we want to distribute entanglement within each of these links independently. And once the entanglement is successfully distributed, what we will do is a joint Bell state measurement here in the middle between these 2 memories, which will now extend the entanglement to the outer memories here. So for doing this, there are three important things. The first one is that we need to send photons in fibers, so the photons need to be at telecom wavelength. So we need to have a quantum node which is entangled with the telecom wavelength photon. Then we need to have heralded creation of entanglement. We need to have a signal that tells you when the memories or the nodes are entangled. And finally, then you need to be able to store this entanglement in some quantum memories to allow for while you wait for one link to be ready, and to store the entanglement, waiting for the other links to be also ready. I just want to mention also that there are also type of quantum repeaters which are not based on this heralded entanglement, which are based on error correction, but which necessitate slightly more sophisticated resources. So if we want to do this kind of quantum repeaters based on heralded entanglement, what do we need? Well, for the nodes, first of all, you need to have an efficient interface between the matter qubits and photonic qubits. And as I said, this interface should be done with photons at telecom wavelengths to be sent in optical fibers. We should then store the qubit for ideally very long time in the matter node. And ideally, you also want to be able to store not only one qubit, but many qubits to boost the quantum repeater rate. And finally, you would also need to have ideally some quantum logic between the local bits, as this will be some small quantum processors. If you want to put some numbers, it's a little bit difficult to put exact numbers here because it depends a lot on the architecture. But we can safely say that we will need efficiency which of the order of 90% for the interface. We would like to have storage time between a few hundred microseconds to a few hundred milliseconds, depending on the architecture. And typically, you would need to have a lot of modes stored, a lot of qubits stored, like more than 1,000 modes. So there are a few approaches that have been proposed. Some of them are based on atomic ensembles, like cold atomic ensembles, for example, or rare earth doped crystals. We will talk about this last one today. And then there are also quantum nodes based on single atoms or single ions, Carl centers in diamond, and a newcomer in the field also with single rare earth ions in optical cavities. So these first two one here on the left are very good for doing multiplexing because they are ensemble based. And this other nodes on the right will be good also to do quantum processing because they have this ability to do gates between qubits. So we are studying these nodes in two different quantum flagship projects. These nodes here on the left are studied in the Quantum Internet Alliance. And this last node, the single rare earth ion, is studied in the Quantum Flagship Project Square. I'll be talking today mostly about these nodes here on the left. So in the Quantum Internet Alliance, there was a lot of progress recently. We have seen, for example, the first multi-node quantum network that was done in Delft very recently. At MPQ in Munich, they have demonstrated a quantum repeater node with a fidelity high enough to perform quantum key distribution. So here the idea is that you have two atoms into an optical cavity. Each atom is entangled with a photon. You send one photon to Alice, the other photon to Bob, and then you do a Bell state measurement here in the middle. And they have seen some advantage of using this versus just sending one photon from Alice to Bob. Also in ensemble-based memories, we have seen a lot of progress. In Paris, in Julien Roy's group, they have demonstrated the most efficient quantum memory. Actually, this one is based on cold atomic ensemble for entanglement. In Geneva, they have realized a long-lived solid-state qubit memory for up to 20 millisecond storage time. And finally, at ICFO, we have demonstrated a quantum repeater link, which is in principle extendable to longer distances. I will talk more about this last experiment in a few slides. So most of these systems actually create light in the visible range. For example, NV Center at 637, doped crystal at 606, rubidium at 780, and so on. And so what we would like to do is of course, to use telecom photons. So because this at this wavelength here, you have a lot of loss in optical fiber, so you cannot send directly these photons into optical fiber. So where we would like to be is here in the telecom C-band, where we have a very low loss. And so there are different ways to do that. First way is to use actually a material which directly works at telecom wavelength, and there was some work done with erbium-doped crystal that work directly at telecom wavelength. However, the performance are not so good yet. The performance in the visible. Very recently, there was also some work using single erbium ions that were performed at NPQ, Princeton, and ICFO. And I think we'll hear some talk about this in one of the next sessions by Andreas Heiser. So if we want to stick with, let's say, the most efficient memories and nodes we have so far, one way to go to telecom wavelength would be, for example, to do quantum frequency conversion. So we want to convert the photons emitted by the node to telecom wavelength. Another possibility could be to use a source of entanglement, non-degenerate, where one of the two photons is now resonant with the quantum memory, and the other photon is directly at telecom. So let's look a little bit into these two possibilities. The first possibility to do quantum frequency conversion, this could be done, for example, in a nonlinear periodically poled waveguide, where you have your photon that you want to convert, that you mix with a very strong pump at omega-2, and then you will generate either sun or frequency difference generation. And so there have been a few examples of that in the last few years. I highlight here this one, which was done also in the context of the Quantum Internet Alliance. This is some work done in Innsbruck, where they have a calcium ion from which they generate a photon, which is entangled now with the ion. And this photon is a polarization qubit that they now convert using two different PPRN converters. And they can send it into optical fibers up to 50 kilometers. So they have really long distance entanglement between the trapped ion and the photon. And there have been also a lot of other works using different systems, also, for example, single atoms, other experiments with single ions and NV centers and atomic ensembles. This is one example also that we have done at ICFO using quantum frequency conversion, where we have been able to do quantum communication between very disparate quantum nodes. What we have done is that we have created a qubit in a cold atomic ensemble. We have converted this qubit to a telecom photon. And then we have back converted it to visible wavelengths to be stored in a solid state quantum memory. So this shows that we can really, in principle, communicate with two different types of quantum nodes using a single photon at telecom wavelength. Okay, so then the other approach is to then use a quantum memory and a photon pair, non-degenerate photon pairs. So this is something that we study at ICFO, and in our case, we use a solid-state quantum memory based on praseodymium-doped crystals, and we use, let's say, for the specialists, we use the atomic frequency COM memory. What you need to do for now is that this memory is temporally multimode, meaning that you can, if you store a train of single photons, you will retrieve also a train of single photons, and it has a bandwidth of around 4 megahertz. So the photon pair source in our case is based on spontaneous parametric down conversion in a cavity. So the crystal is put inside a cavity to be able to generate these non-degenerate photon pairs with one photon pair resonant, one photon resonant with the quantum memory, and the other photon is at telecom wavelength direction. And so we have a bandwidth of around 2 megahertz. And so first thing that we can do is we will detect a telecom photon, then we will herald a single photon at 606 nanometer that we will then store in the quantum memory. So we can store it in the excited state. You can see here, this is the signal, retrieve signal from the excited state. But we can also put control pulses that bring now the collective excitation down to spin states. And then in the spin states, we have this echo here. And then we also show that this actually preserves also the entanglement carried by the photon pair at the beginning. So we store one of the entangled photons, and at the output, it's still entangled. The energy time is still preserved with a high fidelity. And there will be a talk about this later, I think this morning by Samuele Grandi. Okay, let's now see how we can entangle two of these nodes, remote nodes. So the idea now, we have two of these nodes with, again, one photon pair and one memory for each node. We will pump the two nodes coherently, and they will emit a photon pair in coherent superposition. And then, so mode A and B are stored in the quantum memory, and mode A prime and B prime are coupled into an optical fiber and detected here at the beam split, mixed at the beam splitter and detected here at the central location. So when we have a click at the central location here, this beam splitter then erases the origin of the photon, and what we know, we don't know if the photon came from the source A here or from the source B. And so what we end up with is an entangled state with a photon stored in memory A and no photon in memory B, in coherent superposition with the other possibility. So we have a 1, 0, 0, 1 state. So this is an entangled state, entangled Fock state. It's heralded because when we have signal now that tells us when we have the entanglement, and then we can proceed with measurement and with the follow-up. So this scheme is very similar to the famous scheme proposed by DLCZ in 2001, and which has been done with cold atoms in a couple of occasions, with the nice add-on that it can optimize the wavelength now. So one photon is resonant with your memory, and the other photon is directly at you can also use then this temporal multiplexing capability that we have here. So this multiplexing is actually very important for the following reason. Because we need to have a heralded entanglement, this takes some time to have the signal if the two nodes are far away, because the photon needs to travel all the way down the fiber to the central station, and then the classical information has to come back to the node. And this takes the time L0 over C, where L is the distance. And if the nodes are very far apart, for example, 100 kilometers, then this will limit the repetition rate to around 2 kilohertz. So this is very low. And moreover, the success probability for one shot is also very low. So one solution then is to use a multi-mode memory and to be able to store multiple qubits inside your quantum memory. So then you can try many times per communication time, and you can basically boost your communication rate by a factor of n, where n is the number of modes. Okay, let me now show an example how we can do that, doing this entanglement using the remote quantum memory. So we have now these two nodes, which are in two different laboratories separated by 10 meters. We pump them with a common laser, and then the idler photons are combined here at the beam splitter. We have here a phase shifter to control the phase that we have, that is acquired by the photons from the source to the node. And then when we have a click, in principle, we have this entangled state here. But now we need, of course, to verify that we really have this entangled state. And so for this, we basically need two things. First of all, we need to show that we are in the single excitation regime. And second, we need to show that we have a coherent superposition now between these two terms, this 1, 0 and 0, 1 terms here. So for that, we recombine the two modes. And then we can make a nice interference fringe, which show that we now have a coherent superposition. Then we can build a density matrix with all of this measurement, and we can show that we have a concurrence which is larger than 1, which proves that we have entanglement between the two memories. And what we see here is that actually there is a very big vacuum component. This is because these events that you see here are really detected events, so photon that we retrieve from the memory and we detect. And because we have some loss in our optical setup, this increases the vacuum component. But I stress here that this vacuum component in the repeater architecture will not be bad for the fidelity, but will also only reduce the efficiency of the scheme. So to have an idea of what we could have if we now remove this vacuum, we can compute an effective fidelity where we have a fidelity of 92% in that case. So this proves that we have been able to create a single collective excitation, which is shared along these two crystals, which are in that case 10 meters apart, but which could be in principle longer. A few comments. So this is heralded by a photon at telecom wavelength, which means that in principle, indeed, you could travel long distance in optical fibers. The heralding rate is actually quite large. It's actually the largest for this kind of experiment with long-lived memories. And also we have been able to use multiplex quantum memories, up to 62 temporal modes in that particular case. And the entanglement was stored for up to 25 microseconds in the excited state of this crystal. So this would allow up to 5 kilometer distance. So overall, this the message is that this experiment is in principle directly extendable over longer distances. And one thing which is important indeed is this multiplexing. In that case, we had just 62 temporal modes, but we could also use different degrees of freedom to try to have more modes and have more multiplexing. So let's imagine that we have 20 temporal modes. This is something that we can do very easily. We could also use frequency modes, so we could create quantum memories at different frequencies in the crystal. And this is an experiment that we have done recently where we have stored 15 modes, but let's imagine for now 20 modes. And we could also use spatial modes, for example, by using arrays of quantum memories, using integrated memories, for example. This is a recent example where we have been able to demonstrate a fiber integrated quantum memory with this system. And there will be a talk about this afternoon as well by one of my students. And so we could easily know, but we could do, it's possible to do like a 10 by 10 arrays of memories, so we could have 100 spatial modes. So in total, this would leave us 40,000 modes, which would bring, of course, a significant potential for the improvement in repeater rate. Okay, let me now conclude. So we have seen that there was a rapid progress actually in several platforms, and I have shown some examples in the solids in principle, in particular that we can build a link, heralded entanglement between two memories, which is heralded by a photon at telecom wavelength, and so in principle it's extendable to longer distances. The next challenges, first of all, we need to improve very significantly the node performances in terms of efficiency, in terms of storage time, and in terms of multiplexing. It will be a very challenging task actually to have a memory that have at the same time, let's say, all of these parameters very high. Then we want to move on to build high fidelity long distance quantum repeater links. We want to make entanglement swapping between repeater links, which has not been shown up to now. And also for this, we will need basically to build more practical, deployable, and autonomous quantum nodes. And for this, we will use the very strong European industry that makes very, very good stabilized lasers, cryostat, control electronics, or integrated optics. And finally, it's very unlikely that one particular node will be able to perform everything, all the tasks. So I think it will also be important in the future to interface between different kind of nodes, between, for example, this kind of ensemble-based repeater nodes and for example, single ion or single NV centers node for processing. And also, actually, something which will be important is to make an interface between satellite links as well. So we have a lot of challenges ahead. I think we are very well placed in Europe to tackle these challenges and to have in the next 5 to 10 years a first demonstration of a long distance quantum repeater. So thank you for your attention. And let me thank my group as well.
Thank you very much, Hugues, for this very interesting tutorial with a lot of new results. As we agreed, questions will be taken in our joint session at the end of these three talks, at these three plenaries. And so thank you. And it's now my pleasure to introduce the next plenary speaker, that is Professor Pascale Senellart. She's a professor at the French Center for Scientific Research and also has a role in the spin-off Quandela. So without further delay, I would like to give word to Pascale, please.
Thank you so much, Paolo, for the introduction. Can you see my slides? Yeah?
Yes, indeed.
Thank you.
Thank you.
So thank you so much for the introduction. Thank you for the invitation for this session. In this talk, I will discuss our work on the developing resources and more specifically quantum light resources for quantum communication. This work is done at the Center for Nanoscience and Nanotechnology. It's a joint CNRS University Paris-Saclay unit, and you can see here below beautiful pictures of our new building. In this group, we develop quantum light sources based on semiconductor devices. So here you see a typical chip, which is electrically controlled. If you zoom in with a microscope, you see these wheel-shaped structures, which are actually optical cavities. And at the center of each of these cavities, we have an artificial atom, a semiconductor quantum dot that can emit one photon at a time. So with this, we are working in the idea to provide quantum light for many applications: quantum communication, quantum computing, quantum sensing. What's fantastic with quantum light is that there are many flavors of it. You can play with discrete variables or continuous variables, and you can use all kinds of degrees of freedom to encode the information: path, polarization, time, photon number, etc. So in this talk, I will address only discrete variable aspects. So in practice, single photon sources or a source of true single photon pairs, entangled photon pairs or more entangled photons are very interesting for long distance quantum communication, like Hugues just made this beautiful introduction. It's very interesting to have entangled photon pairs to achieve entanglement distribution from a satellite. And on the ground, using the fiber network, you can also use this kind of experimentation that was reported recently, again by a Chinese colleague, using twin field QKD. And in both cases, if you have true quantum statistics for your pairs or your single photons or even your superposition of photon number states, you can go to a higher rate and longer distances. Where single photons are obviously needed, and Hugues just reminded us of that, is in quantum networks. You have two architectures that are possible, the one that Hugues just presented beautifully, and there are beautiful progress in this direction, those based on memories. But there is also another architecture that has been introduced later, which is based on measurements and large states of light where many photons are entangled together. So again, here, there are lots of challenges for people like us trying to provide interesting quantum light sources. So let me spend a few minutes explaining how our technology works. So how we can fabricate efficient quantum light sources. And maybe in one slide, we have some very basic metrics to check whether our source will be efficient or interesting or not. There is the efficiency of the source. We are discussing here pulse light source that should provide one photon at a time. And one metric to be able to compare all kinds of technologies is to consider the probability to actually have one photon when you want it. This is an important metric for us because we are targeting the idea that one day we can make a deterministic source. In the meantime, we are measuring the probability to actually have one photon. The source should not emit more than one photon, so we measure that with a second order intensity correlation function, G2. And to make this Bell states measurement that Hugues was referring to before, we need the photon to be highly indistinguishable, which means in the pure quantum state, to undergo the quantum interference. So we fabricate these kind of devices providing this kind of nice metric using semiconductor quantum dots. So they are indium gallium arsenide quantum dot for the talk I will present here now, the result I will present here now. They emit around 920 nanometers, but the community is moving to other wavelengths, which are more interesting for quantum networks, and there is always the possibility to frequency convert as well. These dots are inserted in an optical cavity made of two mirrors here confining light in the vertical direction and in a pillar shape that confines light in the other direction, like in a fiber. And overall, with this system, where we have a technology to position precisely the atom in the cavity, the artificial atom in the cavity, we use cavity quantum electrodynamics to have an efficient collection of the photon. We play with acceleration of spontaneous emission, the so-called Purcell effect, which ensures that most of the light is emitted in the cavity mode with a fraction which is given by this factor here. The faster we accelerate the spontaneous emission, the closer to the deterministic source we are. And then we make sure that the photon goes into the first lens. And with that, in 2013, we managed to have sources with a brightness and efficiency around 80%. To obtain indistinguishable photons that will be useful for quantum network, where you can make Bell states measurement and things like that, we needed to have more efforts on our system, and especially to reduce all kinds of decoherence introduced by the solid-state system. The first noise we got rid of is charge noise by inserting the system in a diode structure, where by applying a voltage, you simply sweep away charges that would be fluctuating around your emitter. Then we implemented the tools that are very standard for atomic physics, coherent control, to deterministically bring our emitter in the excited state. And you see here Rabi oscillations that are damped only by spontaneous emission. We want the photon to get out of the cavity, so we have a very fast spontaneous emission decay that damps our Rabi oscillations. And finally, we understood that we can actually get rid of most of the coupling to phonons by, again, playing with the Pascale effect, accelerating the emission in the zero phonon line, where the quantum dot has no time to interact with the vibration of the crystal before emitting a photon. So with that, with these various tools, and I'm presenting here a result in my group, but it was really a collective progress in the community. We have, the quantum dot community somehow brought a new generation of quantum dot sources that could be useful for quantum technologies and especially quantum communications. So here is a map of the source that we would like to have. The efficiency should be 1, so the deterministic source is up there. The indistinguishability should be 1, so the ideal source is up there. With a single parametric down-conversion source, you have a compromise between the efficiency and the indistinguishability. And the quantum dot community had made some progress, but it was either bright or indistinguishable until 2016, where we managed to finally get both features at the same time, and we are now on this vertical axis. This is in this context that we created Quandela, that now commercializes these sources. You can see here now the second version of their product, where you actually don't need to be an expert in quantum optics to operate the source and use a single photons. But our work is not finished as a community. We are still trying to go upper, and I want to advertise here work that we published this year, where we gain another factor of 2 in the source efficiency. And there are also beautiful work by the group of Richard Warburton, who also managed to make another impressive leap in efficiency. So what I wanted to share with you today is maybe some news that you are not so familiar with, is the idea that with these sources, we are now working on generating cluster states of light, and first linear cluster states. So we have 2 ways of doing that. The first way is with an idea proposed by Agai Heisenberg from the University of Jerusalem, Hebrew University of Jerusalem, which is perfectly suited to our quantum dot sources, which generates trains of single photons. And the idea is that we send these photons into an untangling apparatus, where the photons can go into a loop to wait for the next one to come, and they meet together here and get entangled. So we implemented such a scheme with, on one side, our sources, on the other side, the setup developed by the group of Agai, which is very small and compact and very simple, actually, very little number of resources, which is why it's very elegant and efficient. You have the photon generated from the dot entering this circuit here, where you have polarization, a bunch of polarization controller, a delay loop here, which is kind of a very basic memory, and a polarizing beam splitter. So this is a non-deterministic entangling gate. It's a probabilistic gate that works 50% of the time. And the output, you get a linear cluster state encoded in polarization for photon distributed in time. And in the box, we also have some apparatus to do some analysis of the state. So we did that. You can look at this, you can consider this circuit also in terms of logic gates. So here it's a sketch for 4 photons. For each photon, we have first a preparation gate, an Hadamard gate, then an entangling gate with a preceding photons, then a phase gate and an Hadamard gate in the loop. And this goes on for as many photons as you want, and at the end you have some analysis. So we did that for 2, 3, and 4 photons for now, with different kind of sources with higher brightness or indistinguishability. You can see here some witness for non-local interference that we measure. At the bottom here, you see the state that they correspond to, and various contrasts depending on the indistinguishability of the photon we play with. The group of Agai has derived some entanglement, bonded entanglement witness, and they are all negative here, which means that we have generated photonic cluster state up to 4 photons. And this was the very first demonstration, not even using efficient detectors, and we have a lot of losses here, and we are now working to scale that up. And there are also ideas to bring this scheme to more than one-dimensional cluster state. I want to mention that we are also working very hard in my group, but in many groups of the quantum dot community, to provide another way to generate cluster state in a deterministic way. This is based on the schemes that was proposed by Thierry Rudolph and Nathanael Lindler in 2009, where you use this local spin of your emitter as a local quantum memory. It doesn't need to be a long-term memory, just a good enough memory so that you can generate many photons entangled with the same spin. So on the quantum dot side, we can do that using one laser to generate the photon and the other to control the spin. So we are working on that. I want to mention that we are making progress in this direction. One of the challenges here is that you want to have access to the polarization degree of the photon, and this is not easy in our system where you need to get rid of the laser in a very tiny device. So we are happy because we found a new excitation scheme that preserves very high indistinguishability and high brightness, and that allows for polarization encoding. This is based on phonon-assisted excitation. And these are data showing that we are now very simply monitoring a single spin per session in our quantum dot. We find with absolutely no optimization yet, 20 nanosecond spin coherence time for a photon lifetime of 200 picoseconds. So we could play and generate a few photon entangled with this system. And we are working right now on tripartite entanglement generation. Last thing I wanted to share with you is about our work on photon number encoding. There are many situations in quantum communication where you are making single photon interference and playing with 0+1 photon superposition, where often attenuated lasers are used, but you still have the two photon components that comes in. We can actually generate pure superposition of 0 and 1 photon in our system. And I will open the last part of this part on the photon number entanglement. So when we do coherent control on an atom, we know when we have this Rabi oscillation that we create a quantum superposition of the ground and the excited state of the atom. What we inquired is whether we can translate this to the photonic state that we generate. Can we create, just like that, a superposition of the ground and, of the 0 and 1 photon component of the electromagnetic field? So actually we do. To test that, we do we either what we call revisit the Hangul-Mundell interference, or you can see this experiment as a self-homodynamic detection scheme. And what you can see here is the idea that when we send two superposition of 0 and 1 photons here, basically, if you calculate the state of the output of your beam splitter, you have more components than what you anticipate when you just play with single photon state. You have, of course, the 2-0-02 state that we well know, which is the Hangul-Mundell interference. But now we have also a 1 photon component of the state. And this 1 photon component actually depends on the relative phase between the two input photons. The two input wave packets. So actually what we find here is that if we look at the single counts here, we should have oscillations in opposite phase on the two detectors, which are actually having a visibility proportional to the vacuum population of the state. And this is, of course, in the ideal case, but if you consider that you don't have a perfect system, you have some limited purity in the frequency domain or in the photon number basis, you expect to have also oscillation with the visibility, which is actually controlled by the vacuum population, your purity in the frequency domain, which is basically the mean wave packet overlap, and the parameter defining the purity in the photon number basis. So if we observe oscillation, it means that we have both purity in the photon number and frequency basis. And this is actually what we observe in the quantum dot system when we set our excitation pulse around pi/2 here. And if we look at the single count on the detectors of the outputs of the Hangul-Mundell interference, this is time, but basically it means that's freely evolving phase in our setup. We see these very beautiful anti-correlated oscillations that demonstrate that we actually generate photon number superpositions. We can extract the visibility of this oscillation as a function of the pulse area. And with this analysis, without more details, we could show that we have a purity in the photon number basis, which is above 96%. So we are able to generate pure quantum superposition in the form of that is sketched here, where the population are controlled by the pulse area and the phase is controlled by the phase of the laser. You can use this to encode the information for us if you want. Last development I want to share with you, with no detail, just to give you a glimpse of our latest work on this matter, is the generation of photon number entanglement, just exciting twice our system. Let's excite our atom and put it in the excited state with the first pi pulse. There is spontaneous emission decay, which basically means that after a time delta t, after the excitation, the light matter field is entangled. We have the atom excited with 0 photon with this coefficient, and the atom in the ground state with 1 photon with this other coefficient. And it's not a statistical mixture, it's a pure quantum state. Which means that if I look at what happens around halfway during the spontaneous emission decay, I have this superposition with equal probability of 0 and excited state and ground and 1 photon. And on the photon field, it means that I have either emitted no photon or 1 photon in an early time bit, an early time mode that I can define. Then the idea is just to add a second pulse at this very moment. And it's basically, oh, sorry, it's a mistake here. It's an atom gate. We just flip the atom. If it was already in the excited state, we bring it back to the ground state. And if it was in the ground state, we will bring it back to the excited state. So here, I just perform a gate on the atom. And then I let again the system evolve through spontaneous emission. And now the first part of my state tells me that I will have no photon either in the early or late time bin. And the second part will give me a second photon emitted in the second time bin. So basically, with this, we show that we can create a Bell state encoded in the photon number basis over 2 time bins, the phi plus state, which is 0, 0 plus 1, 1. We can visualize this state doing second order intensity correlation. So here you see a map that shows actually the 2 time beats and the fact that the photons are emitted in different time beats. And we could derive a fidelity to the Bell state of 80% in this first implementation. Details are found in this publication. This is limited just because our system is too fast. We are actually having too fast emitters. If you want to do this experiment with an atom, you will have plenty of time to distribute spatially your photons and have higher fidelities. And we also have some ideas that maybe we can play with many pulses to generate more sophisticated states of light, like the one I've just sketched here. And with this, I think I'm at my time. I need to stop. Thank you for your attention, and also thank my beautiful team of very brilliant young researchers who did all this work. Thank you.
Thank you very much, Pascale, for this very interesting tutorial talk. And our third tutorial speaker today is Professor Markus Haspenmeyer from Vienna University. And welcome Markus here, long time no see, to give his talk. Markus, please.
Thank you very much, Paolo. The pleasure is likewise. And I will start my talk in a second. Apologize for a delay here. There we go. So I would like to go back in the beginning to what Paolo said in his introductory remarks. So our quantum technology today really relies on research on fundamental questions that have been done over the last decades, and vice versa, of course. So it's if you want, symbiotic relationship between them. One requires the other. Progress in one results in progress in the other. So, and speaking from Vienna, the example that I would like to share with you obviously involves Schrödinger. So the example that I want to give is a discussion that Schrödinger started with Sommerfeld a long time ago on the, well, one of the questions that went on back then between all of the founding fathers of quantum theory relating to the meaning of the wave function. What do we describe out there with the wave function in nature? And Schrödinger gives in this letter to Sommerfeld this wonderful example of a heavy mirror interacting with a photon. He says here, schwerer Spiegel and Lichtquant. And he describes actually how by interaction, those two evolve into an entangled state, and how by controlling the states of the mirror, one can control the state of the light. Well, the inverse, using control over the light to control the state now of a solid state object, is essentially what has emerged out of this example that Schrödinger designed as a Gedanken experiment to address some of the most fundamental questions of that time. Nowadays, due to the progress in micro and nano fabrication, in micro optics, in optical technologies, integrated optical technologies in general, we are now at a position where we can combine optomechanical interactions, radiation pressure interactions on micromechanical systems, as is shown here, with the toolbox of quantum optics, which nowadays falls under the collective name of quantum optomechanics. I give you the idea in a nutshell. The idea is very simple. Instead of now just having a heavy mirror on which you have a single photon reflecting, what you do is you enhance the interaction by placing a second mirror to form a cavity, and then you have radiation pressure induced interactions onto this moving mechanical element in this cavity. So essentially the change in the cavity energy results in a radiation pressure dynamics inside the cavity that allows now to essentially exchange energy between the mechanical object and the cavity field, and that in turn allows you to modify both the states of the radiation field inside and outside the cavity and the states of the mechanical objects. So normally this would be the single photon case, which results in a strongly nonlinear interaction. This has not been achieved yet, so you can drive your cavity either with a just coherent state or a squeeze state. You get a linearized interaction, and the quantum optics audience among you already recover here in the interaction, or discover in the interaction, the famous two-mode XX coupling that can result now in either coherent energy exchange in a beam splitter interaction or two-mode squeezing to generate the entanglement that Schrödinger already indicated. So in a nutshell, the fundamental simple physics picture can be caught in a inelastic scattering picture, a photon scattering off the mirror, a photon basically driving the cavity can now scatter into the cavity in a Raman scattering process. For example, if it's red detuned, it can scatter into the cavity by getting some extra energy, which it takes from the mechanical system, which is known as laser cooling. And a blue detuned photon needs to get rid of energy, so it will scatter a photon into the cavity by at the same time coherently exciting the mechanics and the cavity, which is a two-mode squeezing interaction, and generates entanglement. So in that way, now we have a full quantum optical toolbox that allows us to control both the state of the light and of the mechanics inside such an optomechanical system. And obviously realizations are manifold. The most simple way would be to connect a moving mirror, Schrödinger's heavy mirror, as the end mirror of a Fabry-Perot cavity. But also, for example, here in this microtoroidal cavities, you see here whispering gallery modes that act via radiation pressure on the boundaries and can lead to mechanical interactions. You can have dispersive coupling of elements to fixed cavities, and you can even have the mechanical element form the back end of a capacitor, for example, which is part of an LC circuit, which in turn is again now a microwave resonator. And so all the optomechanical interactions also apply in the microwave domain. Let me just give you a very brief example. Back then, when we started to look into that, so the original idea was exactly to use this idea of laser cooling that has been, of course, already developed in the AMO community, where we generated these micromechanical systems made out of optical coating alone, such that you have high reflectivity. You can use a second mirror to form an optical cavity. Here you see the cavity mode. And then by detuning the cavity, you can, through the cavity, resonantly enhance the anti-Stokes scattering process, which means you laser cool the center of mass motion via radiation pressure. The initial results were not so promising. We were able to cool by a factor of 10 from room temperature. The reason being simply that the mechanical systems were too bad, because the cooling rates were countered by very strong heating rates, simply through low mechanical quality factors, having phonons dissipate back into the systems. And so what happened in the years to follow was essentially a combination of mechanical and optical engineering to improve the mechanical quality, such that the decoupling of the system from the environment became better, and also the optical quality in order to enhance the interaction with light. And it was finally then in a collaboration with Oscar Painter, who pioneered photonic crystal cavities as optomechanical structures, that we are able to cool into the quantum ground state. I give you a very brief glimpse here. The idea is the following. With these photonic crystal cavities, essentially it's a 1D photonic waveguide where you have periodically holes drilled in, such that they periodically modulate the index of refraction in a way that a photon propagating along the structure essentially sees a Bragg rating, it's back reflected. You do the same on the other side, you put a defect in the middle, such that when you input light here through an adiabatic taper, for example, you have two mirrors and you form a cavity. And at the same time, of course, if the structure is freestanding, you also have mechanical motion, and which is co-localized with the electromagnetic field mode enhancement, and in that way changes in the density of the material strongly influence the cavity frequency, which gives you an extremely strong optomechanical interaction. At the same time, since this is a nanomechanical structure, the frequencies are rather high. So if I have now this mechanical mode at 5 gigahertz, I put it in a dilution refrigerator, then I am automatically freezing out all the thermal excitations, and I'm in the quantum ground state of motion of the mechanical structure, which means I can now combine it with optical pumping in order to do essentially to achieve quantum optical control over single phonon states of this mechanical system. So just here as an example, here's the photonic crystal structure. Here is adiabatic fiber taper coupling to the cavity, and we can pump now the cavity either by a red or blue detuned drive. As I already said in a Raman scattering picture, if I pump in a blue detuned manner, the only way I can create a photon into the cavity, I can scatter a photon into the cavity, is by creating a phonon in the system, and and vice versa, a red detuned drive will extract a phonon, which of course leads to sideband asymmetry if I want to determine temperature and so on. And now I can, of course, once a photon is scattered, you see I can now measure the single photons that I extract. So I can condition my experiment now on the detection of either a Stokes or anti-Stokes scattered photon, which leads to several possibilities. I can now, for example, do intensity interferometry, so I can deposit a phonon on the initially ground state cooled system and can demonstrate now that the state is non-Gaussian. I can also have two mechanical oscillators, and this in a similar spirit that Hugues already showed, and I can now create a phonon in a delocalized manner, generate entanglement between two distant mechanical systems, which is essentially a solid state implementation of the well-known DLC-Z protocol, with the advantage here that this is now a silicon-based photonic structure. Let's say, resonant interaction wavelength of which can be designed, okay, simply by designing this photonic structure. So this is and this ideally suited, of course, for the telecom band regime. Now, over the last 15 years, I would say, the worldwide achievements in the field were, to say the least, astonishing. I think it's very fair to say that by now we do have extremely good control over solid-state mechanical resonators in the quantum regime. And I already told you a few examples. Here's an extended list of examples. Quantum ground state of motion, either by really methods of laser cooling or brute force cooling, as I just showed you, generating quantum squeeze states of motion, where one took ideas really from the trapped ion community and realized them here for the first time with mechanical systems, and also control over non-Gaussian states of motion up until towards generating entanglement, either between light and mechanics or between two mechanical systems. And needless to say, this also resulted now in a manifold, is resulting at the moment, this is happening as we speak, in a manifold of different applications, starting in the domain of precision interferometry, where the methods of optomechanics have been used either for creating new coating technologies, or as it is shown in a recent paper, to increase the sensitivity in gravitational wave detectors. Other topic is in the domain of transduction between the microwave domain and the optics domain. So the outstanding goal here is to really have conversion between single microwave photons, single optical photons, and back, or at least information stored in these photons, using a mechanical system as a transducer. The quantum sensing is a big topic, and here the main idea and the big advantage of such solid-state systems is, of course, that you can functionalize them. So you can have, as I showed you, using photonic structures, you can couple the mechanical modes to photons, but at the same time, this system can be piezoelectric. So this is how you can couple it also to, for example, the microwave domain. The system can be magnetic, so you can also couple it to spins, and so on and so on. And this is a big advantage of such mechanical systems as transducers, and you find in literature several applications that are being pursued at the moment. At the same time, of course, I told you, I showed you up there how light interacts with an optomechanical cavity, and it turns out that this optomechanical element simply poses as a nonlinear medium. So what you can do with such a structure is dispersion engineering, and you can do that on a chip. So you can have many of those on a chip, and that allows you to do on-chip signal processing, both in the classical or in the quantum domain, and in the optical and in the microwave domain. And there's also many suggestions how to use mechanical systems for fundamental physics, and I will come back to that at the end of my talk. Now, there has been a development lately, now that we have solid-state mechanical resonators that are on chip, that are clamped under control. There has been interest in extending coherence times significantly. And one way to do that is to borrow the really almost perfect coherence times that people have in the molecular and atomic interferometry community, where, because of the free fall of atoms or molecules in a high vacuum, you essentially don't have any localization processes. So, if you now want to combine this long coherence times with large mass as given by the solid-state systems, what you could do is you could simply levitate your solid in an external trap. This has many advantages. First of all, you're not suffering anymore from internal friction, because you now, the motion of solids, the center of mass motion is now dictated by the external trap, and you can shape the external trap as you want. So basically, instead of just having a harmonic potential, you can now have any arbitrary potential shape, and you can even switch it off and go to your a free evolution environment. Now, an example, this is something many of you are well familiar with, how to levitate particles. Well, if they're dielectric, you can simply optically levitate. If you have a focused laser beam, then it is the intensity profile of the beam that provides the potential landscape. So if you have now a focused Gaussian laser beam, then for small displacements, you will have a 3D harmonic confinement through the Gaussian shape. And this will allow you now to keep, like in our case here, 150 nanometer diameter glass particles inside a laser beam. Now, if we want to go now towards the quantum regime, the first thing that we could do is we can just adopt the ideas that I showed you before. We can just put a cavity around the particle and then force the scattering into the cavity in order to extract energy. And this is an example of a recent experiment. You see here's the trapped particle in the optical tweezer. You just put a cavity around it, and now you stabilize the cavity frequency with respect to the tweezer such that the tweezer is detuned by the mechanical frequency, which means now that the cavity can resonantly enhance the anti-Stokes scattered photons along the cavity direction. And that allows you again to laser cool the center of mass motion down into the quantum ground state. So the cavity essentially acts as a reservoir. If you do not want to have a cavity, then another thing you can do is you can directly read out the particle. So you have the particle here in front of your tweezer. You can use the forward scattering, for example, to obtain XYZ information and to use that to stabilize the particle motion in a parametric feedback. This allows you now to stabilize the particle to very low pressures. In the cavity case, the cavity already stabilizes, so it's not so much necessary to do that. The next thing you can do is you can now also look at the information you get in the backscattering, because it turns out the most information about the position of this particle is provided in the backscattered plane. So what we can do now is, so we add this down here, which is nothing else than a confocal imaging in the backplane. And if you do it right, then you can measure the position with a sensitivity close to the Heisenberg limit. And if you combine that now with a state space model, also then known as a Kalman filter, then you can use the information about the particle in real time to obtain the quantum trajectory of the particle. So we do a real-time tracking of the quantum trajectory close to the zero-point motion of the particle, because our position sensitivity is close to Heisenberg limited. And of course, once you can follow a phase-based trajectory with a quantum ground state resolution, you can also feed back that information and stabilize the particle and cool it just by a feedback to the quantum ground state. And what you see here is actually a picture of our glass particle kept in a room temperature environment where its center of mass motion is cooled to the quantum ground state of motion. This also has an interesting aspects for sensing, for example. So using this real-time state estimation, you can also now be sensitive to small disturbances that are not taken care of by the Kalman filter. Okay, so what you see here, for example, is a small kick in the time data that is processed in real time. And this is still work in progress, but it seems that we are here in this experiment are sensitive to kicks of a single gas molecule on our particle. And this has in general quite interesting aspects for sensing of weak forces, in particular transient forces. Now, there's a whole trajectory now going from where we are at the moment, basically having single particle control in the quantum regime of levitated particles. And there are many routes to go from here. In particular, once one extends it to the two-particle domain or to larger systems, you see many possible applications in the domain of many particle systems, macroscopic quantum physics, and also metrology. I give you two very brief examples. One is, I told you before, we can also manipulate the potential landscape that the particle sees. And this is work that is being done right now here in Vienna by Mario Ciampini and Nikolai Kiesel's group. They are looking you see different spatial profiles they can set in real time. So they can now basically shape the potential landscape, have a double well, for example, have tilted double wells, inverted potentials, and they are now investigating that to study non-equilibrium memory effects and stochastic thermodynamics and so on. Now, to conclude, let me humor you with another outlook where this could go. Now that we have control of solid-state particles in the quantum regime, could we, coming back now to Schrödinger and the fundamental questions, could we address a very fundamental question that I would claim we did not have access to before, which is the question, does gravity require quantum description? And one possible ways to address that is to use quantum sources as quantum systems as sources of the gravitational field. And I think that solid state systems in a quantum regime provide a trajectory for that. And in particular, one needs to address those two questions for the future. How small can we make a source mass and still measure a gravitational field? And how massive can we make a quantum system and maintain coherence? Which is what we are currently following up in Vienna. So I already showed you about our bottom-up approach, studying the quantum regime of nanoparticles. We also have a top-down approach where we really want to find out what is the smallest gravitational force we can measure. We recently demonstrated gravity from a 1 millimeter gold sphere, and now we're pushing very strongly to measure the gravitational field of the mass of a Planck mass. So let me conclude here. I think what I wanted to do is I wanted to go in a full circle from originally interest in fundamental questions that developed into quantum technologies, which in turn, of course, enable to address new questions in fundamental science. And I do hope that I'm preaching to the choir here, but I really think it's important to point out once more, it is research into fundamental questions that is the driver for innovations. It is the research in the innovations into technologies that we need to then enhance industry, industrial support, startups, and which then will flow back again into enabling our fundamental science questions. Thanks a lot.
Thank you very much, Markus, also for your inspiring tutorial talk. Well, first of all, we have a few questions from the audience. First is to Hugues. Could you please comment on the fiber non-linearities, especially temporal care in the use of memories, from Osman Malchoglu?
So I suppose then you're talking about using Kerr nonlinearities for making sources. So indeed you can make
use of the memory for I mean, has it store the qubit as it goes, and if it essentially decrease the quality of it when it has to be stored, essentially.
So we don't see any effect of decreasing the fidelity due to the Kerr nonlinearities. So what you can use Kerr nonlinearity for is for making sources of entangled photons. This is a possibility. However, it's the nonlinearity that you get into this Kerr this Chi3 nonlinearity is a bit too low for our purpose, because what we need to have is to have very narrowband photons. And so for this, we need to filter down we have basically 4 orders of magnitude. We need to filter down 4 orders of magnitude the spectrum of the photons to really go in the regime where we can store them. And so the Kerr nonlinearities are typically a bit too low for our purpose. That's why we use Chi2 nonlinearities for that.
Thank you. Question for Pascale. Why the visibility drops with the count in the photon number encoding by Emanuele Distante?
Yeah, so actually this is, I will not show my slides again, but you can understand it by the fact that basically in a Hundel experiment, when you look at the single counts and you play with 0 + 1, the single counts oscillate because it's as if you had a 1 photon interference in the Mach-Zehnder. And it's basically the more vacuum you have, the more you are close to the situation of having just one photon. You send two, a proposition of 0 + 1, but this signature comes as a single photon interference coming from two fields. So this is why it's all the largest when you decrease the one photon number population and the vacuum population increases. I hope it helps.
Thank you. Another question for you. Fusion-based quantum communication based on those small entangled resource states is attracting attention. What do you think are the challenges that you will face?
Yeah, so there are many challenges here, but I think also very exciting prospects. So there are different ways of generating cluster states, a small one, and then you fuse them both for quantum computation or quantum communication. You can do everything with heralded sources, and then you need to pile up millions or hundreds of sources, switchers, routers, etc. And this is a way to do it in a scalable way. And I think this is, for instance, what the quantum computing company SPI Quantum is developing. So this relies heavily on technology. The other approach is to use this local memory, but if the memory, so it doesn't need to be a beautiful memory with millisecond time scale, but if you want to have high fidelity cluster state, we still need probably 2 orders of magnitude between the photon lifetime and the memory lifetime. And right now we are a bit on the limit here, but again, in the quantum dot community, and there are also other spin systems that could be interesting for that, but the quantum dot so far have produced the best photons. There are groups, for instance, in the group of Metrology in Cambridge, who now are able to master beautifully the decoherence induced by nuclear spins. So we combine their expertise with other expertise like ours of collecting photons and having high indistinguishability. It could be interesting.
Yes, thank you. And this also goes with another question that I would like to turn to Hugues about the storage time of the memories that say limits the range. And there's a question from David Shaw. What is the prospect of improving the storage time?
Yeah, so indeed, in our current experiment for the entanglement, for example, we had a storage time of I think 25 microseconds. This was only storage time for storage in excited state. But what we could do and what we're working on now is to transfer these excitations to the spin states, where there, in principle, we could have much longer storage time. So people have shown that you can actually store classical images for up to 1 minute in this kind of crystals. So there is prospects to go to let's say much longer storage time. It's not at all straightforward though to transfer let's say the classical storage to quantum storage, because what we need to do is to use some sort of dynamical decoupling, for example, to remove the dephasing in the spin states. And this induces a bit of noise. And of course, what we don't want to have noise to add noise to the quantum memory. We want to keep, let's say, if we add 1 photon of noise, it's already too much. No? So we want really to keep the lowest noise as possible. And so this will be a challenge. But in principle, there are prospects for storing for let's say, at least tens or hundreds of milliseconds. Actually, people have shown, there is an experiment now in China where people have shown that you can store coherently, it's still classical, but coherently for up to 1 hour in the similar crystal. And so there are really prospects in this kind of red dot material to get to very long storage times.
Thank you. So I think it's all for the questions. And now we'd like to have a few minutes with you speaking in this panel discussion of an opportunity that we have here, say, take a chance on the future. So how do we see our field going in 10 years? I mean, Markus has pointed out very nicely the loop with also an effective image, the loop that we have among between experiments, technology, applications, and back. Okay. He also mentioned a very important things that in the basic results that you have shown, he said we can functionalize the system in a way to make it sensible to environment, sensible to vibration, to other things, okay? And which means that it may provide an information that is generated on some place that maybe needs some state of light that is most suitable to pick that up, and needs a way to be conveyed all the way to, for instance, a gate in which you have this remote qubit that is carrying information of a remote system that is measured against a local qubit for computing, for monitoring, for many applications. So that's a vision. But within this, I would like to ask you, how do you see your research field in 10 years, if you can use for a moment the crystal ball, that so will inspire the efforts to make? I mean, we are in a panel discussion. I think we may use some inspiration for that for our public. Please, in the sequence.
Okay, so well, I think one of the really important vision that I would like to convey is probably what I would like to have in like 10 years is really this kind of quantum network I was mentioning in the beginning, where we will be able to distribute entanglement between remote parties. We will be able to store this entanglement in say entanglement banks or something like this, where you could really distribute this entanglement and store it for later use. For some applications that now we know some applications, I'm convinced that in the future we will have other applications for that. This entanglement could then be transferred, for example, to quantum processors to increase the potential of quantum processors, but also to communicate to quantum processors from far away, for example. And I think we can really have the potential to at least to progress towards this. So at the beginning, of course, the progress we will go not directly to 1,000 kilometers. We will need to step-by-step progress. We'll still to progress a lot on the quality of the nodes. But at the end, I think we will eventually reach a state where we will be able to distribute this entanglement, also using interplay, I think, between, for example, between satellites and quantum repeaters. I envision that quantum repeaters might be useful for distance of up to, I don't know, maybe a few thousand kilometers or continental distance. If we want to go global, probably we will need to use satellites. Maybe we could also use quantum repeaters in satellites. That's also a possibility. But that's really where I would like this field of quantum communication to go, to be able to distribute entanglement between any 2 point of Earth.
The entanglement bank is conveying the message. And by the way, if quantum communication is connecting system at the most fundamental level, and information is the new gold for this century, that's really the case. Call it entanglement bank. Pascale, please.
Yes, so maybe I will. I of course I completely agree with Hugues' vision, and we are all here trying to contribute to this vision. I will bring two maybe additional ingredients on the technology side, and then maybe I will take my Quandela hat here. I think there is all this proof of concept, and we know that, like we emphasize it, there is a very integrate link between technology and science progress, and so we need to make everything reliable, robust. So my dream, for instance, I think for the quantum community will be to have a very compact system that could generate all kinds of quantum light state that can be brought from one place to another with everything inside in a very reliable way. And if we take this joint, very ambitious scientific vision and technological requirement, maybe we can work faster. And I think this will where I think the community is heading progressively, combining both scientific and technological expertise. The other ingredient I would like maybe to share with you that I think would be fantastic for our community is maybe have a community where we mix all the ideas more efficiently. I think there is all these protocols based on memories, measurement, cluster state of light, quantum memories, etc., are continuous and discrete variable, and there are many resources that actually would probably just be faster, more efficient if we combine ideas. So I would like that our community in 10 years is way more mixed up, so that new ideas come out, and that I'm sure we need, if we look back in history of classical communications, to make the change that Hugues is envisioning.
Thank you very much. And indeed, this call for essentially for keeping a large space for experiments and basic research in the area beside the application. And of course, I remember our master pointing this to us like Untitled for many years among others on the necessity of keeping the research activities in the front light, essentially. And Markus, what about you?
Yeah, I'm coming from the other side, and I guess addressing then more the sensing community. So I expect, and I'm super confident, so that this research that I addressed at the end, really asking these questions at the interface between quantum physics and gravity, using the capabilities we have now to drive extremely massive, well, from a quantum perspective, objects into the quantum regime and try to measure gravity. I think this will, just the attempt of doing it will result in so many interesting insights from a technology point of view. I mean, obviously there's the large science goal in the end, addressing this question, does gravity require quantum description? But already now, seeing what it requires from a technological standpoint, we need to be able to isolate tiny forces in a regime that we have not done before. So we will have really new experimental methods to measure short-range forces between on small scales of small objects. We will get a new understanding experimentally on these things, on short-range forces, which means we will be able to control them better. We will, on the large side, we already see that. We have now also more massive systems that we levitate because of the large mass and the very good, I showed you the precision sensing of position with ground state resolution. If you add mass now, we have an incredible inertial sensor. So also there, and all of that you can package in a small, into a small volume. So I think also there, just the attempts of going in that direction will lead to new technologies, new insights that will have immediate impact on several fields.
In this sense, also, it's needed to keep the technology transfer active from the pioneering research work. Yeah, which is of course also something that needs a dedicated efforts because it's not at all obvious that this may happen up to a, say, high TRL level. Okay.
And as Pascale said, it requires the information exchange between different communities on all levels. Definitely.
Yeah, I think this is something that we have to keep in mind very well, especially in these hard times. We are meeting in front of a screen, and it's definitely not the best way of doing it. So I think we are almost done with the time. No, we are done with the time. And so I would like to thank you very much for the very inspiring and informative talks and for being with me in this plenary. So I think I would like to give back the word to our organization and thank you, all of you, for listening. And
thank you, Paolo.
Hugues and Markus have to be with me this morning.
Thank you.
Have a